All right. So in the third week of our course, we are going to learn about some algebraic relationships between the factors that we found from compound interest tables. So we are just going to use the extended notation to explain the algebraic relationship between interest factors. And before that, we are going to start with another type of cash flow series, which is called the gradient series. Now, the outline is as follows. First, we are going to explain the gradient series. So once we cover that part, then we can safely talk about the relationships that we can create between these interest factors. So these relationships can be listed according to this classification. Once we classify all these relationships, or chapter for this week will be concluded. Okay, so what is a gradient series? At this point, we need to understand what a gradient series is. So remember, in the uniform series, we have a time horizon of n investment years, and in the end of every year, we observe the same amount of positive or negative cash flow. So all of the arrows were one-sided, and they were having the same length, which means the size of the payments in the end of each year were the same. Now, in the gradient series, we have a different situation. We have a linearly increasing payment amount. Okay, the size of the cash flows are increasing linearly with a gradient. Okay, so let's read it. It deals with a series of annual payments in which each payment is different than the previous one by a constant. The gradient series that consists of n years start with a zero amount cash flow in the end of the first year, which is called the base amount. So a zero is the base amount. And in the end of the second year, the payment size increases to zipper plus G. So G is the size of the increase in the payment. And in the end of the third year, the payment size increases with respect to or compared to the previous year again G. So it becomes a 0 plus 2G, the payment size in the end of the third year. So if it goes like that, in the end of any kth year, the payment size will become a 0 plus k minus 1G. And finally, in the end of the nth year, the payment size is going to be 0 plus n minus 1G. So what we call to such a cash flow structure is a gradient series, gradient cash flow series. And A0 is the first, which is called the base amount, and G is called the gradient amount, okay? And the first gradient increase is observed in the end of the second year, okay? So we need to be very careful at this point. In a gradient series, the first gradient increase should be observed in the end of the second year, and such a cash flow structure is called a gradient series. So why this is practical? So we have solved many questions related to uniform series in the previous week. Here we are explaining a new series, which is called gradient series. Instead of having a constant amount of payment in the end of each year, we are observing a linearly increasing structure or cash flow structure in the end of each following year. So why do we study such a gradient series in engineering economics? Because this is much more practical. So, you know, because of inflation effects, instead of taking constant payments, people would be interested in increasing size of payments in the each subsequent year, right? So because of that reason, such a gradient series is also practical to observe either in the payment plans developed for loans or credits, or if you are planning a retirement, for example, this can be your retirement payment plan. So after you retire, this is just going to be your retirement salary end of each year, increasing by an amount in each following year. So this is not the last series cash flow structure we are going to learn in this course. We are also going to study another type of series, which is called geometric series. But here at this point, we are studying this linearly increasing gradient series. Now, our objective here is to calculate the future value or the present value of such a cash flow diagram. So if I am going to repay my loan, which I have borrowed right now, with such a payment plan, what should be the A0 amount and G amount? Or if I invest or deposit these amounts of cash flows in a savings account in the end of each year, what would be the total amount that I have I accumulate in the savings account in the end of n years? So we are going to answer such questions. Just like the previous week, we are going to convert such cash flow diagram to the future value or the present value under the assumed compounding interest rate every year. Okay. Now, how we are going to approach the problem? First, we will try to convert this gradient series of cash flows into an equivalent uniform series of cash flows. So this is our plan, the first plan, where we observe a gradient series which, with a base amount of A0 in the end of the first year, and each subsequent year, the size of the payment increases by G compared to the previous year. Now, instead of taking this payment plan, I would like to take another payment plan where all payments are equivalent to each other for n years. So I would like to develop a uniform series. Now, we already have a uniform part in this gradient series, but we also have a part starting from second. So my objective here is this. How can I convert this gradient part to another uniform series in which we are going to have payments of size A in the end of each year? Okay. So I would like to convert these G values. So if I am given this G value as the increase of the payment size in the end of each year, I would like to convert this to a uniform series, which are going to be equal amounts in the end of each year to A. And the other uniform series, the base amount A0, will also be here as well. Okay. So how am I going to convert this G value to A value if I would like to change my gradient series to a uniform series? That is the question. Now, to do that, what I'm going to do is I'm just going to calculate the future value of the first plan. So how am I going to calculate the future value? First of all, we are going to decompose this gradient series into two parts. So the base part, A0, will already conform to a uniform series property, right? So it already has a uniform series property, and the remaining parts are going to be decomposed as well. So we are going to decompose the first step. And here in the first step, we have a gradient series at constant amounts starting from the second year until the nth year. And at the third step, we have another gradient series starting from by the end of the third year until the end of the last year, so on and so forth. Actually, in each step of these stair-shaped arrows, we have a series starting from the kth until the end of nth year. Okay, we are going to calculate the future value each step. Now, the first step, A0, conforms to the properties of a uniform series for n years, and the future value of this uniform series can be computed by multiplying the uniform series compound amount factor f over a under I% interest rate for n years. Plus, let's focus on the second step here, the second step, G. Okay, for how many years we are observing this uniform series? Actually, we are observing it for n minus 1 years. Be careful, it is starting from by the end of the second year. And for n minus 1 years, a uniform series is happening in the second step. And you see, we are multiplying the second step's uniform payment size G with again series compound amount factor under I% interest rate for n-1 year, not n years this time. So we can calculate the future value, second step in this stair-shaped cash flow diagram. For the third step here, we have another uniform series which consists of n-2 years. So we are going to assume that the second year is year 0, the third year is year 1. Therefore, the nth year is going to be year n-2 for this uniform series. So we are going to multiply the second step's g value with, again, uniform series compound amount factor f over a under I% interest rate for n-2 years. And it is just going to go like until the last step. And for the last step, we only have a single g. We are multiplying it with f over a under I% interest rate. However, my friend, I mean, this coefficient f over a for 1 year will always be equal to 1 in any way. Basically, even though there is a multiplication here where this single g is multiplied with a compound amount factor, that compound amount factor, if you look from the table, will be equal to 1. Okay, so by extended notation, we have represented the future value of this gradient series of payments in the end of year n. Now, let's just convert each extended notation to its formula. So we know that the uniform series compound amount factor is formulated as 1 plus I to the power n-1 over I. And in every other compound amount factor, the only thing that is changing is the number of years. So the power here n reduces to n-1 here, to n-2 here, and so on and so forth, until it reduces to n1 here. If you are careful here, if you calculate this formulation, 1 plus I minus 1 over I will be equal. But still, we are trying to develop a general structure for this formulation. Okay, so the first part is written already here. Now, for the remaining part, we are just going to apply a trick here. Now, you see this g value in the first component is multiplied with 1 plus I to the power n-1 and divided with I. And also, it is multiplied with -1 and divided with I. Okay. In every other component, g is multiplied with the first part of the numerator and also with -1. So we have a minus g over I coming from each component. And how many components do we have here? We have n-1 terms, right? Starting from here until here, we have n-1 components. And in each component, we have minus g over I. Therefore, we basically calculate all of these minus g over i's for n-1 times in a single step and add it in the end of this function. And for everything else, we have g times 1 plus I to the power n-1 over I, so on and so forth. So the power of 1 plus I is decreasing 1 by 1 until it becomes 1. So, and then we are going to do another trick. So this n-1 g over I is actually n g over I, and there is also a plus g over I, right? Plus g over I. So instead of subtracting n-1 g, we subtract n g over I, but the additional subtraction of g over I can be added in the end of this summation. So g 1 plus I over I plus, we can write g over I minus g over I. And if we do that, you will realize every component where we start with g here, we will have a g over I, and the remaining multipliers would be 1 plus I to the power n-1, 1 plus I to the power n-2, so on and so forth, until the last multiplier will become 1. And we also have a subtraction of ng over I. Now, in the last week, you have learned that this finite summation is called the geometric progression. And the sum of this geometric progression was equal to what? The uniform series compound amount factor, right? So the first component is directly written here. The second part, where we have a multiplier of g over I, and the sum of the geometric progression, which is again 1 plus I to the power n-1 over I, minus over I. Now, in the last, we are just going to keep this A0 times the uniform series compound amount factor as it is. Plus, in the last two terms, we have a common multiplier of G. So G is just going to be taken outside the parentheses. And then we are just going to do a small algebra between the multipliers of G in the first and the second component. And the resulting formula would be G times 1 plus I to the power n minus 1 minus ni over I square. So this is the future value of the gradient series. This is how we calculate the total accumulated amount. If you make deposits in a savings account under I% interest rate compounding yearly, according to a base amount of A0 and the gradient size of G, which is the observed increase in each subsequent year after the first one. Okay, so this is the future value of the first plan. Now, I am just going to calculate the future value of the second plan. So remember, this was my second plan, and I am going to calculate the future value of it. And the future value of the second plan is simple. We have basically two uniform series, A0 and A. Simply, we can sum them up. A0 plus A is the payment size in the end of each year. So if we multiply this with the uniform series compound amount factor, then we will have A0 times the uniform series compound amount factor plus A times the uniform series compound amount factor. Okay. Now remember, my objective was I would like to make this plan and this plan equivalent to each other so that for the size of G, what should be the equivalent payment size, uniform payment size of A. So here, what I'm trying to do is I'm trying to convert the G, the gradient, to a uniform series. How can I do that? By making the future value of the first payment plan and the second payment plan equal to each other. So remember now, in the previous page, we have computed the future value of the second payment plan. This was F2. As A0 times the uniform series compound amount factor plus A times the uniform series compound amount factor. And in the other page, where we have developed the future value of the first payment plan, we have stated that it was equal to A0 times the uniform series compound amount factor plus G times the algebraic formula that we have developed in that. Now, if the two plans' future values are going to be equal to each other, and this will require, since the first terms are the same, this will require A times the uniform series compound amount factor and G times this formula should be equal to each other, right? So for a gradient series, the gradient size then be converted by taking this uniform series compound amount factor to the other side. It can be converted into what? It can be converted into a uniform payment amount. So if you do not want to pay in a gradient series of cash flow, and if you want to pay in a uniform series of cash flow, and this is how you are going to convert your gradient amount into the uniform payment amount. By multiplying the G with 1 plus I to the power n minus ni over I times 1 plus I to the power n minus 1. Now, with a small algebra here, you can easily develop that A over G, which is called the gradient series factor, that converts the gradient amounts to uniform amounts, is going to be formulated as 1 over I minus n over 1 plus I to the power n minus 1. Okay, and the extended notation for the gradient series factor, which converts the gradient amount to uniform amounts, is A over G under I% interest rate for n years in ordinary brackets. Again, the formula is 1 over I minus n times n over 1 plus I n to the power n minus 1. Okay, now either you can use this formula again for problems related to gradient series of cash flows, or you can use the compound interest table to for your value from the. Now this is our first question to solve. Here, an engineer is planning for a 15-year retirement plan. In order to supplement his pension and offset the anticipated effects of the inflation, he intends to withdraw a $5,000 at the end of the first year and to increase the withdrawal by a $1,000 at the end of each successive year. Okay, so here's the thing. So right now it is year 0, and the engineer is planning for a 15-year retirement, which means for the following 15 years, he would like to take or withdraw some money from a savings account as salary, okay, as a retirement salary. But because of the inflation effect, okay, because of the anticipated effects of inflation, he knows that if he gets his retirement salary in uniform series, in the end of the 15th year, the amount is not going to be worth anything, because every year the money is losing its purchase power due to the inflation. So what he thinks is he must take an amount that increases with a constant size, constant gradient in the end of each year compared to the previous year. Okay, so his plan is this: in the end of the first year, he's going to take a retirement salary of $5,000. In the end of the second year, it is just going to be $6,000. In the end of the third year, it is going to be $7,000, so on and so forth. Every year, the salary is going to increase by $1,000, and in the end of the 15th year, obviously, it is going to be equal to $19,000. Okay, so the question is this: if he wants to take these withdrawals from his savings account, right now, how much money should he have? So right now, he needs to put some money, the principal amount, into that savings account, so that amount is going to gain interest over time for 15 years. As of course, as he withdraws money, the remaining amount is going to gain interest. And what should be the principal amount that he needs to deposit right now so he can take his retirement salary in this manner? Okay, now what we know about the savings account: the savings account applies an interest at a rate of 6% per year, which compounds annually, which is written here. So basically, here we have a question, and this question can be converted in this cash flow diagram. This cash flow diagram basically summarizes everything for us. So we are looking for an equivalent principal amount right now that should be invested, so that in the following 15 years, the engineer can money at the amount that he describes here, and savings account is subject to a 6% interest rate per year. Okay, so how do we solve this problem? First, we need to decompose this gradient series. So we observe a gradient series here, right? So because it is linearly increasing, decompose this gradient series into the base amount and the gradient amount, and you can easily observe that the base amount 5,000 is here, and the gradient size is $1,000 for each consecutive year. So A0 is 5,000, G is 1,000, and the interest rate is 0.06 as decimal, and the number of investment years is 15. Now, we are going to identify the equivalent annuity for the gradient series. So I am just going to do that. So instead of this payment plan, instead of this gradient form of payment plan, if the engineer was planning a uniform series of retirement salary plan for 15 years, what would be the equivalent A amount if we are going to take these amounts in uniform series? So we already have a formulation for that. We can use our formula by multiplying the gradient amount 1,000, the gradient series factor A over G under I% interest rate for n years, and or n is 15 and or I is 6%. And we can do that by using the formula in the first place. Okay, so through the formula, we can plug in I as 0.06 and n as 15. So we can identify the equivalent of $1,000 of gradient is $5,925.98. So let's make it 5,926. Which means, my friends, so instead of observing $1,000 of gradient size here in the end of every year compared to the previous year, instead of that, we can take 5,926, as far as I remember, dollars in the end of every year at constant amount. And both plans are going to be equivalent under the interest rate of 6%. Okay. Now, we can also calculate that value, the equivalent uniform amount for the gradient, by multiplying the gradient series with the uniform gradient series factor, which can be looked through the compound table. And for that, I am going to share the compound interest table with you. Okay, hopefully you can see it here. So what we are looking for is the page that corresponds to 6%. Okay, so for 6%, we have this page, and you see the last column of the compound interest factors belong to the gradient series factor, A over G. And for 15 years of retirement plan, as you can see, what do we have here? 5.9260 as the factor, the gradient series factor. So we are going to use that value and 5.9260 is here, as you can see. Multiplied with the gradient amount 1000, again you are going to approximately get the same value as here. So the formula gives you a more accurate value, but if you are interested in using the compound interest table and a factor that is already calculated approximately, you can also use that. Now, the equivalent annuity is what? Remember now, the base amount remains in the equivalent uniform series as well. So instead of starting with a payment plan of, let's do that to you here, the $5,000 of base amount and an increase of $1,000 in each subsequent year, instead of that, what the engineer can do is to take a uniform amount for 15 years in size of $10,926, because this $5,000 will also be remaining in the other part, and the grade of increases is converted to the uniform amounts of $5,926 in the end of every year, each year. So this is the equivalent annuity. Now the next step is what? We know that this gradient series is equivalent to a uniform series of $10,926 for 15 years. So if we are interested in the unknown principal amount that we should have invested, we can calculate the present value of this uniform series, which is A prime, the base amount plus the converted uniform series. So this A prime will be multiplied with the uniform series present worth factor under, again, 6% interest rate for 15 years. And that P over A value either can be computed by formula, or again, you can check the table to identify the rest. You can identify A over P. And that 9.7123 would be the multiplicative inverse of that value. And the P value will become 106,116.6. So this means what? If you invest or deposit $106,116.6 right now into the savings account, which pays 6% compounding interest per year, you can either withdraw this money as it gains interest through time in a gradient series form, starting with a $5,000 and $1,000 of increase in each subsequent year. Or you can take your retirement salary in the form of a constant payment amount in the end of each year as $10,926. Both payment plans going to be equivalent to each. And the practice here is how we have converted the gradient amount of $1,000 to a uniform payment size. Once we convert it to a uniform payment amount, then the remaining part is the same as the previous week. We can play around with the uniform series, calculate the future value or present value. So how do we solve the gradient series problems? We solve the gradient series problems by first converting them to uniform series. That's the key. Now we will have another question, the second question here. Again, we will observe a gradient series, but this time this gradient series is a little different. It says, how much money must initially be deposited in a savings account, paying interest at a rate of 5% per year, compounded annually, provide for 10 annual withdrawals that start at 6,000 and decrease by 500 each year. So this time, again, the principal amount is being asked, but this time the withdrawal plan is going to start with a base amount of $6,000. Instead of observing an increase, we observe a decrease of $500 this time. So basically here, the gradient is negative, okay? The base amount is positive, but the grade is negative. In fact, the base amount could have been negative as well. The base amount could have been negative as well. So we have a positive base amount and we have a negative grade in this question. And for 10 years, if we subtract each year payment as with $500, in the end of 10th year, the last payment would be $1,500. Now, how we are going to calculate the present value? This time, the solution procedure is just going to be fast. Okay, we are not going to explain in detail, but the solution procedure is basically the same in the previous question. In this question, the base amount A0 for the first year's payment is 6, and the gradient amount, which is the increase amount in each subsequent year, is minus $500. So this means it is actually a decrease. And the interest rate is 0.05 and the number of investment years is 10. So what is the principal amount? Now, remember, a gradient series consists of two parts. The base part is as in the form of a uniform series A0, and we have a gradient which can be converted into a uniform series as well. And after converting it to a uniform amount, then we can also calculate its present value. So let's handle the uniform series, which is obtained by the base amount of $6,000. We multiply $6,000 uniform payments with a uniform series present worth factor under 5% interest rate for 10 years. And the gradient part is first converted to a uniform counterpart. Remember, the gradient is negative now. And it is converted to a uniform counterpart by multiplying the gradient size with the gradient series factor, A over G, under 5% interest rate for 10 years. And finally, when it is converted to a uniform series, it can also be multiplied with the uniform series present worth factor P over A under 5% interest for 10 years. Okay, so basically here we directly compute the present value of the base, the uniform series obtained by the base amount, and here we are calculating the present value of the uniform series, which is obtained by the gradient amount in the first place. Then it is converted to the present value, right? Now, P over A under 5% interest rate for 10 years is obtained through A over P value, the uniform series capital recovery factor, under 5% interest rate for 10, which is 0.12950. And we are taking the reciprocal of it, the multiplicative inverse of it, converted to the uniform series present worth factor. Here we have the same factor as well, so we are writing it here as well. And A over G for 5% interest rate for 10 years, we need to obtain that value from the table. So I am again sharing interest tables. Now this time I am looking for an interest rate of 5%, and we have A over G in the last for 10 years, it is equal to 4.0991. So if we go back to our presentation file, so you see 4.0991 here is obtained from the table, and the result is 30,505.41, which means right now, if you have $30,505 approximately in that savings account for the following 10 years, under a compounding interest rate of 5%, the money is going to gain interest, but you can withdraw $6,000 in the end of the first year, and in each subsequent year, you can withdraw $500 less compared to the previous year for 10 years. And in the end of the 10th year, your money is just going to deplete. Okay, all of the money will be gone with your last withdrawal. All right, so this was just the end of the gradient series explanation, and I'm just going to continue our lecture in the next video.